Okay, I'm going to do this for class 13. I previously recorded a video where I walked through these. I think I'm going to break them up into smaller segments. So I'm going to do this same problem in 4 different methods. This is from the book, my draft book that I'm writing, the Engineering Dynamics Course Companion, and this is for just a simple linkage that's moving with a velocity VB we happen to know downwards at 1.5 feet per second. And we have the length of 4 feet and 6 feet. It's at an angle of 25 degrees at this instant, and we want to determine the velocity of point C. So it's just sort of like this generic problem. This video will be for the vector math method, which would be doing a formal method to find it using vectors, vector equations. So the first thing that we have to do when trying to solve a dynamics problem is often navigate through what we know and then kind of see the path to what we want to know. So we want to know the velocity of C, but we don't necessarily know how to get there just yet. So first thing we do know is the velocity of B is downwards, and the velocity of A has to be along this line right here. So let's take a look at that relationship between points A and B, and we know that the relative velocity between them could be expressed as omega ABC crossed with the relative position vector, right? So if we want to find the velocity of A and we know the velocity of B, we could say the velocity of B with respect to A is going to be omega, the angular velocity of the whole thing, crossed with the position of A with respect to B. So we know the velocity of A is along the I direction. We know the velocity of B. We actually know the magnitude here, but we know that it's going to be negative VB times J, aligned with the J. And then we have omega ABC, which is the angular velocity. We're guessing it's going to be clockwise, therefore it's negative. We use a right-hand rule where positive is counterclockwise. We know the relative position vector RA with respect to B is going to be this length times the cosine of theta, and it's going to be negative because we're looking at A from B, right? So we're going to the left to get to A. That's why it's negative. Times I plus LAB times the sine of theta upwards, right? So again, that's A with respect to B goes upwards if you want to get to A from B. So we can write this out. We can plug all that back into this equation up in here and get this, and then we could distribute this cross product to both places, and you could see that we have the cross products of the unit vectors against each other, and they turn into the cross of K with respect to I is J. And one way of doing this is a method that I learned, and how I always think of it is that that's I, J, and K. If you use the right-hand rule and you cross J, so you put your fingers upwards with the palm towards, and then you curl your fingers with your palm, it has to be going that way, so your thumb has to point into the positive I direction. The same thing when we go to this other, and we go to K crossing with J. If you have your fingers pointed towards K and they cross towards J right here, the only way they could have it is for your palm to be pointing towards J to be able to cross with fingers pointing towards K, and you want to get to J, your palm has to be actually moving kind of upwards and your thumb has to point in the negative I direction. So that's one way to go about trying to determine the cross product based on the right-hand rule. So if we're writing that thing out, we could see which way this equation has. Now we could group together the J's and the I's, or we could just take a look at the J direction. There's nothing on the left-hand side that's equal to J, and so we have negative VB plus omega LB cosine of theta, all of these things that we happen to know right here. So that we could do is we could take that 1.5 and now we could find that omega is 0.413 radians per second. And in the I direction, so on the I side right here, we can go ahead and we could find what the, with knowing that omega, we can find what the velocity of A is going to be. We didn't need to find that A, but it was worth looking at. Now we can proceed to go find the velocity of C. And so we have the velocity of C is equal to, once again, it's this known one plus the velocity of C with respect to B. By the way, now that we fully know the velocity of A, we could have used that as the reference too, and then this would have been C with respect to A. Plugging in the things that we know, we're keeping the VC as generic right here in the X direction and the Y direction. We can write out this equation. We could put in the things that we know now into this equation, write it out. Once again, we have that cross product thing where we have to distribute them. We're able to find each of these and separate them into I's and J's. And in the I direction, we're able to find what the velocity of C is in the X direction, and we're able to find the velocity of C in the Y direction. There it is expressed, and so it's going to be downwards and to the left, right? That's what we're going to find. The velocity is going to go down like that right there, and we can find the magnitude from the square root of the sum of the squares, and we can find the angle based on a rise over run, or this right here. And I do it without saying negatives inside here because I just know already the quadrant that it's going to be in. This right here is going to be the angle that we're talking about right here. So I draw the answer that is down there, and then I indicate what the quadrant it is with that with respect to horizontal. So that's just going to be the first example, and I'm going to make separate videos from here because I don't think people really pay attention to having a really long video. So we'll pick up with the next method of solving this.